Alright, I'm doing a video about finding angles from a three-dimensional vector to each axis that we have on our Cartesian system. So we've got an x, a y, and a z axis. They're all 90 degrees. They're all orthogonal to each other. And we have some vector r. And this vector r is going to have some x components. So it'll have x in the I hat direction plus y in the j hat direction plus z in the k hat direction. And so these are just variables because we're solving for all possible cases. So if this is my r vector, I just want to point out that I can drop a dashed line to my z direction. I can also drop a dashed line to my x and y. So I just want you to kind of see the three-dimensional aspect of this right here. So r is on a plane that is some combination of z and x and y. So you'll notice that down here we could split this at right angles. We could find our x component, and then we could split it in this direction and find our y component. Let me draw that a little bit better. So this right here is going to be our y, right? Because it's in the y direction, that amount. That's our y. This is going to be our x, the amount that we're going in the I hat direction. And then this component is, of course, going to be our z, which is in the k hat direction. So I just want you to see how we can project this vector r onto all three axes respectively. So the first one to solve by looking at it this way. So here's the question. The question is, what angle does r make with each axis? So in other words, what's the angle that r makes with z and with x and with y? What's the angle it makes with those directions? So the first one, for the way I drew it, which is the easiest to solve, is to find this angle. We're going to go ahead and call it theta. It doesn't really matter what you call it. Theta is going to represent the angle from the r direction. It's going to be the angle between the r direction and the k hat direction. And so you'll notice here that we have a right triangle, and we know two of the side lengths. We know that this side length is going to be the magnitude of r, because this is its magnitude, that's its direction. So this length of that right triangle is going to be r, the magnitude of r. This length is going to be z. And so let's draw the triangle down here to kind of bring it back into 2D space. So here's theta. We know this is the magnitude of r, and we know that this side is z. And so I'd just like to point out that we know of a function that relates the adjacent to the angle to the hypotenuse of the angle, and that's going to be cosine. So we know that cosine of theta is going to equal the adjacent, the z, over the hypotenuse, or the magnitude of r. Now I'd like to remind you now that the magnitude of r is found by using the three-dimensional Pythagorean identity theorem, which states that the magnitude of r is going to be x squared plus y squared plus z squared, all under the square root. So that's what I'm just using shorthand by writing the magnitude of r and saving some time. So now we want to solve for theta, which is the angle that our vector r makes with the z direction. So we're going to take the arc cosine of both sides to get that theta equals arc cosine of z over the magnitude of r. And that's what those two dashed lines, or these two lines, it's like double absolute values. It just means the length. So the length of the vector without the direction. So there's our first result. And the easiest one to find, which is that theta, which is the angle from r to the z-axis, is going to be equal to the arc cosine of z over the magnitude of r. Now we're going to end up with very similar results for the other directions but let's prove this geometrically in our 3 dimensions. So I want you to imagine that I draw a line from the tip of vector r, and I draw it down here to the x component on the x-axis. So go ahead and take a minute to prove to yourself that this angle right here, where this line hits the x-axis, is going to be 90 degrees. Okay, so now what is the angle from r to the x-axis? Well, let's go ahead and draw it in here. We're starting at r, and we're going to the x-axis. Let's call that angle phi. And so now we're going to take this triangle right here, and we're going to draw it in flatland again. We're going to put it into 2 dimensions so that we can better analyze it. So here's our angle phi. We don't know this side length. We do know the hypotenuse is the magnitude of r. So this is going to be a running trend. And we do know that the adjacent is going to be the length of x. So once again, if we wanted to solve for phi, or the angle that r makes with the x-axis, we would go ahead and use a relationship that relates adjacent with hypotenuse. And once again, that's cosine. So we're going to say, once again, that cosine theta equals adjacent, which is the x, over the hypotenuse, which is the magnitude of r. We're going to take the arc cosine again and show that, the arc cosine, or cosine of phi equals x over the magnitude of r. So when we solve for phi, we end up with arc cosine of x over r, the magnitude of r. So that's our second result. And you'll notice a pattern here is that for phi, it's just the arc cosine of x over r, magnitude of r, and for theta, it's just the arc cosine of z over magnitude of r. So you could prove it to yourself, but this pattern does continue. And what we end up with when we want to solve for, I'm going to call it alpha. It doesn't matter what you call it, but alpha is going to be the angle between r and the y direction. If you solve for alpha, you'll find that it's equal to the arc cosine of y, because we're interested in the y direction angle, divided by the magnitude of r. And once again, the magnitude of r is equal to x squared plus y squared plus z squared, all under the square root. So this is a quick thing. You can write this down on your equation sheet. This is a nice thing to not have to derive every time. So geometrically, we proved it, and there's a nice symmetry to them. So when I'm interested in the angle to the y-axis from r, I have y divided by magnitude of r, arc cosine. When I'm interested in the angle from r to the x-axis, this is replaced with x. And when I'm interested in the angle with the z-axis from r, this is replaced with z. So I hope this was helpful, and I'll see you next video.